Welcome to another deep dive. Today we're going to be delving into the world of Tennessine,
Tennessine.
element 117.
Yeah.
And we'll be using excerpts from its Wikipedia page to kind of peel back the layers and see what we can learn about this recently discovered element. And I think it's safe to say that it's captured the imaginations of scientists worldwide for good reason.
Oh, absolutely.
Yeah.
I think what's really captivating about Tennessine is that it's completely synthetic.
Oh, really?
So you won't find it occurring naturally.
Okay.
Anywhere it has to be created in a lab. And even then, it only exists for milliseconds.
Milliseconds.
Yeah, it really pushes the boundaries of what we know about the structure of matter.
So milliseconds, that's barely even enough time to blink.
Yeah.
How did scientists even discover Tennessine if it disappears so quickly? And then how did they even confirm that it was real?
Yeah, well, it all started with this ambitious plan to smash atoms together,
Okay.
specifically nuclei of berkelium and calcium,
Wow.
using a particle accelerator. And the hope was that if they collided just the right speed, they'd fuse and form element 117.
So it's kind of like a subatomic game of billiards.
Exactly.
With much higher stakes, though.
Much higher stakes, yeah. But here's where the story takes a fascinating turn.
Oh?
This wasn't just a scientific challenge, it was also a logistical one.
Okay.
The experiment required a berkelium target,
Huh?
and the only place producing it at the time was Oak Ridge National Laboratory in the U.S.
Oh, wow.
But they had temporarily stopped production, and restarting it was considered too expensive.
So the fate of this groundbreaking experiment rested on budgeting.
Right.
That's not what I was expecting.
It's a reminder that cutting-edge science often hinges on factors beyond the lab.
Yeah.
But a dedicated physicist at Vanderbilt University, Joseph Hamilton, who was collaborating with the Russian team, refused to give up. He kept tabs on the situation, and in 2008 his persistence paid off. Oak Ridge resumed californium production, which meant berkelium could be extracted as a byproduct. So Hamilton seized the opportunity and secured the much-needed berkelium.
That's incredible.
Yeah.
I can only imagine the pressure of transporting a highly radioactive, super rare element across continents. Was it smooth sailing?
Not quite.
Okay.
The berkelium had a short shelf life, so to
Yeah.
speak, because of its decay rate.
Right.
They had to fly it to Russia,
Uh-huh.
and the shipment actually got held up in customs multiple times.
What?
Imagine
Yeah.
the stress,
Oh, my.
a multi-million-dollar experiment hanging in the balance because of paperwork.
That's a scientist's nightmare.
I know.
But it eventually made it right.
It did.
Otherwise, we wouldn't be talking about Tennessine.
Exactly. It finally arrived at the Joint Institute for Nuclear Research, or JINR, in Russia in 2009. And that's when the real work began.
Okay.
They bombarded the berkelium target with calcium ions using their particle accelerator.
Wow.
And months later, in early 2010, they announced signs of element 117.
That's amazing. But I imagine signs of an element don't automatically qualify as a confirmed discovery, especially with something as fleeting as Tennessine. How did they prove that it was really real?
Yeah, you're absolutely right. Detecting hints of a new element and confirming its existence are two very different things.
Yeah.
They had to meticulously analyze the decay chain, basically track how the Tennessine atoms broke down into other elements.
So they're piecing together this element's existence based on how it falls apart.
Yeah.
That's wild.
Yeah, but here's the catch.
Okay.
All the daughter isotopes, the products of Tennessine's decay, were also new to science.
Oh, wow.
So their properties couldn't be used to confirm the initial observation. Talk about a scientific puzzle.
Right.
It took a few more years to really solidify their findings.
So the scientific community needed more concrete evidence before declaring victory.
Precisely.
Yeah.
The key piece arrived in 2011, when one of the decay products, element 115, was directly synthesized.
Okay.
And guess what? Its properties perfectly matched those observed in the earlier experiment with Tennessine.
Oh, wow.
It was the confirmation they needed.
So it's like a domino effect.
Yeah.
Creating and confirming one super heavy element helps pave the way for confirming others.
Absolutely. And the story doesn't end there.
Oh, there's more.
The JINR team repeated the experiment in 2012, creating even more Tennessine atoms, and then a joint German-American team confirmed the findings independently in 2014.
Okay, so we've got multiple teams, different methods, all pointing to the same conclusion: Tennessine is real.
Yes.
And in 2015, IUPAC and IUPAP, the bigwigs of chemistry, officially recognized the discovery.
Yes. And can we just appreciate the name Tennessine?
Yeah.
It's not every day a new element gets named after a region honoring the place and the incredible research institutions that made the discovery possible.
It's a reminder that scientific breakthroughs often involve international collaboration and a fair bit of persistence.
Absolutely.
Okay, so we know it exists, but what do we actually know about Tennessine? That's where I imagine things get really interesting. So
Yeah.
tell me more.
Well, Tennessine sits right below astatine on the periodic table
Okay.
in group 17,
Uh-huh.
the halogen group.
Okay.
So you'd think it would act a lot like its lighter siblings, fluorine, chlorine, bromine, etc.
Right.
But that's where things get really fascinating.
Okay.
Tennessine has a few surprises up its sleeve.
Let me guess. It doesn't quite follow the halogen playbook.
You got it. Well, it's predicted to be a metal.
Okay.
Unlike the nonmetals above it,
Mm-hmm.
it's also expected to be far less reactive than a typical halogen.
So it's a metal that doesn't quite act like a metal?
Yeah.
And a halogen that's not so eager to react?
Mm.
I'm sensing a theme here.
Yeah.
Tennessine likes to keep us on our toes.
It really does. And the reason for all this rule breaking comes down to something called relativistic effects.
Relativity in chemistry. Okay, that's not something you hear every day.
I know, right? But think about it. The electrons in superheavy elements like Tennessine are whizzing around the nucleus at incredible speeds, approaching the speed of light.
Wow.
And all that high-speed motion
Yeah.
actually impacts the element's properties.
So are these speedy electrons like the flash of the periodic table bending the rules of chemistry as we know them?
That's a great way to put it.
I like that.
One of the major relativistic effects is the splitting of electron energy levels.
Okay.
It's like those electrons are being sorted into different energy lanes, if you will, and this directly affects how Tennessine bonds with other elements.
I'm starting to see why scientists find Tennessine so captivating. It's a glimpse into a realm where relativity and chemistry collide. What other quirks does it have?
Well, for one, while Tennessine is predicted to have several possible oxidation states or charges,
Okay.
the Maddox-1 state, which is common for halogens, is expected to be rare for Tennessine.
Wait, so if it's not so keen on gaining an electron, does that even mean it's a halogen? How do we classify something like that?
That's a question that has sparked a lot of discussion in the scientific community. It challenges our traditional understanding of how elements behave and how we categorize them. It really blurs the lines.
Fascinating. So how does Tennessine form bonds if it's not following the usual halogen script?
Well, it can still form covalent bonds, where electrons are shared between atoms.
Okay.
For example, two Tennessine atoms are predicted to bond together, forming a diatomic molecule, TS2.
Okay.
It's also predicted to bond with chlorine, creating Tennessine chloride, or TSCl.
Okay, so it can bond, but those are just two examples. What other predictions have scientists made about Tennessine's bonding behavior? This is where I imagine those relativistic effects really come into play.
You're right, they do. One prediction is that Tennessine monohydride, or TSH, the simplest compound it can form with hydrogen, will have a longer bond length and a weaker dissociation energy compared to other halogen hydrides. It all comes down to those relativistic effects influencing how Tennessine's electrons interact.
So even in its simplest compounds, Tennessine is already showcasing its unique character. It's amazing how these tiny, super fast electrons can have such a huge impact on how an element behaves.
Absolutely. And the differences don't stop. Scientists have also predicted the dipole moments, a measure of how charge is distributed in a molecule for molecules like TLTs and NHTs, which are compounds formed with thallium and nihonium, respectively. These predictions show that relativistic effects can even flip the polarity of a bond, with a negative charge residing on the Tennessine atom in one case and the other element in another.
Wow, it really seems like Tennessine is constantly rewriting the rules of chemistry.
You said it, and here's another prediction that truly underscores this element's rebellious nature. Remember how we talked about those electron energy level splits?
Yeah.
Well, they're so pronounced in Tennessine that they actually influence the shape of its molecules.
Okay, now I definitely need a visual. How can electron energy levels affect the shape of a molecule?
Imagine the molecule TSF3 Tennessine trifluoride.
Okay.
Based on what we know about other halogen trifluorides, we'd expect it to have a bent T-shape.
Okay.
But the predictions show that due to those strong relativistic effects, it's more likely to have a trigonal planar shape, a flat triangle.
So even at the molecular level, Tennessine is defying expectations. It seems like its discovery isn't just about adding another element to the periodic table. It's about challenging our fundamental understanding of how elements behave.
You've hit the nail on the head, and there's another layer to this that's even more mind-blowing.
Okay.
Tennessine's existence, even for those fleeting milliseconds, provides evidence for a concept that has intrigued scientists for decades: the island of stability.
The island of stability, it sounds Mythical. What is it exactly?
It's a theoretical region of the periodic table where superheavy elements are predicted to be far more stable than their neighbors.
Oh, okay.
And this stability comes from the arrangement of protons and neutrons in their nuclei, forming what we call closed nuclear shells.
So it's like those electrons orbiting the nucleus in stable shells, but in this case, it's the protons and neutrons inside the nucleus that are all nicely arranged.
That's a perfect analogy. These closed shells create an extra strong binding force within the nucleus, making it more resistant to decay.
And scientists think Tennessine might be on, or at least close to, this island of stability.
Yes, and that's a big deal. While its isotopes still decay rapidly, they live longer than what was predicted before their discovery. This suggests that the stabilizing effects of those closed nuclear shells are starting to come into play.
So what you're saying is that Tennessine is not just a fleeting wonder, but a potential stepping stone towards creating even heavier and more stable elements.
Exactly, and think about the possibilities. If we can create elements with longer lifespans, we could study their properties in much greater detail and maybe even find practical applications for them.
You know, I never thought about how something so short-lived could have such huge implications for the future of science. It makes you wonder what else is out there waiting to be discovered.
It is, doesn't it? The island of stability holds immense potential, and Tennessine might just be the key to unlocking it.
Before we get too carried away with these future possibilities, there's one more thing I'm curious about. How much of what we know about Tennessine is based on actual experiments versus theoretical predictions? I mean, given its short lifespan, how much can scientists actually observe?
Yeah, that's a great question, and it really highlights a crucial aspect of superheavy element. Research, direct experimentation is definitely limited by Tennessene's fleeting existence.
Yeah.
And the sheer difficulty of creating it in the first place, that's where theoretical calculations really come in.
So scientists are using math and computer simulations to fill in the gaps.
Exactly.
That seems like a lot of pressure predicting how an element will behave before you can even really study it.
You're right, it is a challenge, but it's also incredibly exciting.
Yeah.
Scientists use complex models and simulations to predict all sorts of things, from electron configuration and ionization energies to how Tennessine might bond with other elements and the types of reactions it might undergo.
So these predictions basically guide the research, helping scientists prioritize what experiments to try next.
Exactly. They provide a roadmap of sorts, especially when you're dealing with an element as elusive as Tennessine. And in this case, those theoretical calculations were spot on.
Wow.
They accurately predicted many of Tennessene's unusual properties even before they were experimentally confirmed.
That's a testament to the power of human ingenuity, wouldn't you say, not only exploring the physical world, but also modeling and predicting its behavior in this intricate way.
I completely agree. It's a beautiful interplay between theory and experiment. Each informs the other, pushing the boundaries of what we know and what we can achieve.
Well, we've covered a lot of ground in this deep dive into Tennessine. We started by talking about super heavy elements in general, these giants on the edge of the periodic table that are so difficult to create. Then we uncovered the incredible detective story of Tennessene's discovery, a tale of international collaboration, persistence, and a bit of luck with those custom snafus.
Yeah, we learned how scientists painstakingly confirmed its existence by analyzing its decay chain, even though its lifespan is measured in milliseconds. And we delved into the ways Tennessine bends the rules, a halogen with metallic tendencies, our reluctant electron acceptor, and a molecule shaper, thanks to those mind-boggling relativistic effects.
We even explored the concept of the island of stability, this theoretical haven for superheavy elements where decay is slowed, and the exciting possibility that Tennessine might be our gateway to this uncharted territory.
And let's not forget the critical role of theoretical calculations in guiding this whole endeavor. It makes you wonder what other secrets are hidden within those calculations, waiting for experimental confirmation.
So much of what we've discussed feels almost futuristic, yet it's happening right now, which begs the question, why should any of this matter to someone who's not a chemist or a physicist? Why should you care about an element that exists for a fraction of a second?
Because Tennessine represents something much bigger than itself, it embodies the spirit of scientific exploration, pushing boundaries, venturing into the unknown, and challenging what we think we know about the universe. It reminds us that there's always more to discover, always another layer to uncover, and that the pursuit of knowledge is an endeavor worth undertaking.
It makes you realize that even something as seemingly insignificant as a fleeting element can have profound implications. Who knows what doors Tennessine might open in the future? Perhaps it will lead to new technologies, new energy sources, or a completely new understanding of the building blocks of matter.
That's the beauty of science. It's a never-ending journey of discovery. And Tennessine is a powerful reminder that even the most fundamental discoveries can have ripple effects that we can't even begin to imagine.
So as we wrap up this deep dive, we want to leave you with a final thought. How might our understanding of chemistry and physics change as we venture further into the realm of super heavy elements? Could we one day reach the fabled island of stability, and if so, what wonders might we find there?
These are questions that scientists are actively grappling with right now, and the answers could revolutionize our world. We encourage you to keep exploring, keep learning, and never stop asking questions. Who knows what incredible discoveries await us in the years to come?
And on that note, we'll bring this exploration of Tennessine to a close. We hope you enjoyed the journey and that it sparked your own curiosity about the mysteries of the universe that are yet to be uncovered. Join us again for future deep dives where we'll continue to explore, question, and marvel at the wonders of science. Until then, keep that spirit of discovery alive.